Log on, tune in, find out. Another good idea from Cambridge.
This morning session of this conference in Analytic and Geometric Methods in Medical Imaging. And our first speaker today is Jérôme Darbon from the Colonel Superior de Paris. He's going to talk about network flows and nonlinear discrete total variation evolutions. Please.
Thank you very much. Thank you for inviting me. So the talk will be essentially using combinatorial tools, especially network flows, for essentially non-smooth convex optimization and in particular total variation. So it won't be a lot about medical imaging. It will be if you plan to use total variation as a tool, then this is one way to compute it. So this is, part of the work I do present was done with Antonin Chambol in École Polytechnique, Stan Osher, UCLA, Marc Sigel, and I was supported both by CNRS and a grant from the Navy in the States. So the idea of image processing is you want to process an image with a goal, for instance, removing noise, here Gaussian noise, and to reconstruct an image. So removing Gaussian noise, sometimes the noise is pretty terrible, such as here impulsive noise. You might also want to do segmentation, so find the boundary of an object, so label the pixel of the image. And the idea is to formulate those problems as a minimization process. So the idea is you are given an image, so here F, and you want to reconstruct an image U, that is suppose your goal, and you have two terms of your energy. The first term is data fidelity, which tells you how close the image you are reconstructing U is close to the data F in some sense. So this term, for instance, embed the knowledge you have on the noise, so the likelihood for classification pixel, and you have a second term, which is the a priori in a Bayesian framework, or you call that regularization in a variational one, and then you weight those two terms with a parameter lambda. So this is a huge problem. Bit louder? Okay. All right. So you, this is a big problem because U is an image or a signal, so it's typically, hundreds of thousands of variables, a million of variables of pixels, and it can be potentially non-convex. So assume you have a convex formulation and you assume that U lives in a continuous one, then most of people are interested in finding an epsilon solution. It means you want to find an image, U epsilon, that is close to the optimal one, and you see that through the energy, and you say you want to be at epsilon. So you have several approaches, and for instance, the optimal first order approach of Nesterov that tell you that you can compute such a solution with the number of iterations that is essentially, polynomial with respect to epsilon. But in terms of computational time complexity, this is not polynomial algorithm. In order to have a polynomial number of iteration, then you need your time complexity must be polynomial with respect to the number of bits to describe the problem. And to describe a real number, then you only need log over 1 epsilon. So here you have an exponential gap. So the thing is, you get an optimal algorithm, but the theoretical result is no good. So what you do is essentially you're going to refine the class of convex functions you are dealing with so that you will be able to get polynomial algorithm. More or less, if you want epsilon equals 0, then this algorithm never stops, right? So I was interested in, okay, what can I do to get polynomial algorithm, epsilon equals 0, and what kind of functional I can optimize like that. So I'm not claiming, it will be very specific. I'm not claiming I do all convex optimization, only a subclass of it. And actually it will be non-smooth. So you have also, okay, why I am interested in epsilon equals 0? In that, okay, you want fast algorithm always, but I am interested in exact solution to make a dissociation between the model, or your energy you're defining, and the algorithm to solve this problem. Why is that? For instance, you have a reference here of Winkler, where he does emphasize on separation between model and algorithm, because if you have a bad model, with an algorithm that is approximate and you don't know how close you are from the solution, then you can get any kind of result. And he gives actually examples and cite papers where you cannot conclude anything about the model. So another way to tackle those minimization problem is to use a discrete framework. So U here will be a vector, and essentially this becomes a Markov quantum field energy, a Markovian energies. So one of the ways is to use stochastic methods. Essentially, you design a Markov chain to search over the space, then you embed this process into a simulated annealing process, and in theory, you do converge toward the global optimization. Another approach is to use, since you are in a discrete framework, to use combinatorial approaches. And the idea will be to formulate this energy as a network flow. So let me give you what is the idea. The idea of using combinatorics in that, interestingly, you will have exact optimization by definition of combinatorial algorithm. So the idea is I'm going to work with binary energies, meaning if I have an image, each pixels can either be 0 or 1. And I'm going to map this binary energy into a graph, and then I'm going to make an operation on this graph so that I will get the optimizer of my energy. So briefly said, roughly, in that every time you have a variable, then you will have a node in your graph. Then every time you have an interaction between two variables, then you put an edge. Then you introduce two special nodes. And the fundamental operation on the graph I'm going to use is a cut. A cut is simply a partition of my graph so that every node is connected either to the source or to the sink. So now you say, if I am connected to the source, I will assign 0, to the sink assign 1, and now the idea is, can you relate the cut to the energy? And the idea will be, yes, you can do that. So to optimize the energy, then what I will have to do is to compute the cut. One of the nice things is computing a cut here. We have very efficient algorithm to do that. So that kind of approach has been developed actually in the 70s by Pika and Watliff and some other guys. So they do focus on binary energies, and at the end of the day, what you do in image processing, computer vision, is you are able to put a prior which is the perimeter, meaning you're looking for objects where the perimeter of the object is small. That's the idea. That has been used in statistical physics to study ferromagnetic Ising model, and it has been rediscovered for computer vision by Bokov et al. And I have to say that in this paper, they have very nice extension results for non-convex optimization, approximation algorithm. This paper is very important. The idea here is how can we extend that class of approach to non-binary energies. Okay, so the outline of the talk will be as the following. So I will describe how we can build the graph and how we can relate the graph and the energy to do the binary optimization. Then I will extend to the discrete total variation, which is a non-binary problem. And here we'll have some application for denoising, mean curvature motion, and things like that. And if I have time, I will give you some ideas on how you can do evolution of using total variation flow. But this is much more technical, so I will spend time here, and if I have time, I will give you idea. And it's technical, so I'm not sure we'll do a good job at explaining that to us in a few minutes, but we'll see. Okay. So the idea is you consider, okay, I'm going to have here a computer science point of view. So I forget about energies, I consider graph. So I say, you give me a graph, I have nodes, V, I have some arcs or edges directed, and every time I have an arc, so for instance, here to here, I associate a real number, what we call a capacity. And then you have two special nodes, the source and the sink. Now you define a cut as the partition. So you're going to assign each node to two partitions. So you cover all your graph and they belong either to one side or to the other side.
To help us, can you just briefly say when I have an image, how do I associate what is the graph represent?
This is what I'm constructing right now. So that's why I say right now I have a computer science point of view. I forget about image processing.
Okay.
And then I'm going to build the energy. So that's the goal. So you give me a cut. Once I have a cut, I can associate a number, what we call the capacity of the cut, which is here, I will sum all arcs that are actually in the cut, here, cut by the red line. And so that gives me a number. You give me a partition, then I give you a number. And so one of the goals in computer science is to minimize this quantity. So we say we want to minimize the capacity of the cut. So this is what we call the ST minimum cut problem. Now you have a quite standard reason that says if all the capacities are non-negative, we know how to solve the problem using a duality theorem. I mean, this is the standard min-cut maximum flow theorem, so discovered by Ford and Fulkerson, and actually also by those people, I mean Shannon here in the same year. So you're doing a linear duality to compute the cut. So this is a linear program, so linear objective function, linear constraint. You have very efficient algorithm for doing that. So polynomial, in practice, it's linear time. And what I'm going to do now, this is what the computer scientist people did. Now you're trying to relate what they did to something about energies. So for that, you're just doing basic algebra. So you take what Pika and Watley did, say, okay, what is a cut? A cut is a partition. So essentially, it's a binary assignment of variables. So I say, I'm going to consider binary vectors. So one here will be the source. The source is always in one side. The sink, T, is always in the other side. Now I say every binary assignment here defines a cut. Okay? So you got this vector. So now you shake. I mean, you will formulate the cut in terms of those variables, and you get this. And now you're going to shake a little bit the formula. So what you get is essentially a constant term, a linear term, and a pairwise term, where you have the interaction. Now you say, if you give me a polynomial, a binary polynomial with pairwise interaction, then I can relate this polynomial to a graph. So I can build a graph associated to this binary polynomial, such that every time you give me an assignment, a cut, then the capacity of the cut is exactly an evaluation of this polynomial. So now if you want to minimize f, then it's finding the minimum cut. So you know how to minimize this energy by doing some operation on the graph. So this is the basic idea. And so in terms of energy, then you do like that. So it's essentially linear term here, quadratic term here, and this is what we call, I mean, if you want to solve that in polynomial time, then those numbers must be positive. Think like a Laplacian. Essentially, this is a Laplacian. I mean, binary Laplacian. And this is what we call in statistical physics the Ising model. I mean, the ferromagnetic Ising model. All right. So what we can solve is essentially you want to find a set, and so you say I want to minimize the perimeter, and for each pixels you have some recall terms that are essentially linear. So we want to extend that to non-binary energies, and this is essentially the total variation. I mean, the natural extension is the total variation. Okay. So just to, so far I had computer science point of view, I lived in a discrete world. Here just to show you that you can do that in infinite dimension. You can be continuous and you can still do that kind of things. So it will be more abstract just to show you and to convince you that you can do it, but if you discretize everything, then it works the same. So this is kind of magical because sometimes, you know, discrete and continuous worlds do not like each other, but here it's fine. So the idea is I had perimeters, so I'm going to define what I call a perimeter. So for a perimeter, essentially, you need to be able to, I mean, you work on set, so except some, I mean, you have some technical continuity stuff. Perimeter of empty set of the whole world is 0, and essentially a perimeter is this combinatorial combinatorial property, namely the sum modular property. This is what a perimeter satisfies. So we say any kind of function that satisfies that, we call it perimeter. Now, how do you define total variation? So I'm not going to say it's L1 of the gradient. At the end, you can see it like that. But one way to define TV is to extend your perimeter through the Correa formula. Namely, you give me a function u, I threshold it at level lambda. So for each pixel, I will know if I am above or below lambda. That gives me a set. I compute the perimeter of the set, and I do that for all possible thresholds, and I do integrate. And this is how I define my total variation. So from perimeter, you go to TV through what we call the Correa formula. So, okay, so you get back the standard properties of TV. Now you say, if you give me a total variation, then I can associate a perimeter. Essentially, what you do is you compute the total variation of the characteristic function of your set, and that defines the perimeter. So you can go back and forth. The idea is, this has been done in many different areas. So we've been doing that in analysis. If you are in combinatorial community, you talk about unary representation and Lovat's extension, and also in game theory or fuzzy logic, then the thresholding is an alpha cut, and the extension is called the Schocker integral. So these are exactly the same operations. The only difference is, do you live in the continuous world? Are you quantized or not? And you replace integral by sum, blah, 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 and this is exactly the same concept. And in signal processing, this has been done in mathematical morphology, so or stack filters. And you do exactly the same kind of procedures. So what is the total variation? So you have several examples. So this is the standard one weak formulation when you live in a continuous world. You can define non-local functional, like that. So this is what we will consider, essentially. You give me two variables, I take the difference, and I put absolute value. So it will be essentially the L1 of the discrete gradient. And you convey that by a non-negative number. What's very important is, this is a standard discretization of TV. You take the gradient along one axis, the gradient along the other one, and you take the little L2 norm of that. Then this is not submodular. It means all I've been saying is not true. So if you want to do numerics with that, then all the theorem I'm going to show, for instance, if you show that a theorem using that, when you do this numerical approximation, it will fail.
So that's a gap between the continuous model and the discrete.
That's one of them.
Which you can't solve.
No, I don't know how to solve it. But here, for instance, you have nice properties. You say that if you refine the number of grids, then you have a gamma convergence toward this model. When I do that here, then I do converge, and you would saw to a different TV, not this one. Okay? Okay. So now just a little bit of analysis. You consider geometric problem. So it means you find a set A. And what is A? I mean, A is a set, and you want to minimize the perimeter of A, and for every point of your domain, you have a weak term, V. So V tells you if you want to be in the set or not. And so you want to find the optimization, the solution of this problem. Now I'm claiming that if you order the weak term here, then you will have a monotone property. You will have an inclusion of the solution. If you give me an order here, then I have an order on the solution. So there are several proofs. With the Sigel, we did a very complicated one, I guess, using complete techniques from Markov chain. Chambol came with a very simple proof. If you love variational stuff, it's 2 lines and it's done. And also, interestingly, you have also an algorithm that does exactly show that. An algorithm to compute a cut. The way they compute the thing shows that you have exactly this property. So you have several different ways to prove that. What can I say about TV? So I had perimeter, I go to TV. So you say, I put TV, and then here I'm going to put a a quadratic separable term. So it's essentially the Rudin-Oshofat-Emi model. Now, assume that you have a solution of this problem. Let's call it U. And so I'm going to threshold it at the level lambda. So you have strict threshold, soft threshold. And then what you get, that gives you a set A. And this set will be a minimizer of this geometric problem. So if you minimize TV, you threshold it, then what you get can be seen as a solution of a geometric problem. Again, perimeter plus linear term. And so you can even show that this is the minimal and maximum solution. I mean, you can also describe how the set is behaving. And once you have that, then again, as for perimeter, if I order my image here, then I will order the solution. So you have a monotone property. So it does transport to TV. So what can you do with that? Well, one thing is, if you have a geometrical problem, perimeter problem, then you can minimize TV, and then you threshold, and then you get your solution. But you can go backward. So to minimize the ROF energies, then you're going to solve a series of perimeter problems. And what you will get is every time you solve such a problem, then you get one level set of your function. And so if you do that for enough level set, then you will reconstruct the function, because if you know all the level sets of your function, then you know the function itself. So this is what you're going to do. So how can you minimize a perimeter problem? Well, this is what I just described before, because the perimeter will be this term, which is exactly good. Then you have a linear term here, so it's perimeter plus separable data fidelity, so you use what we described before. So you know how to reconstruct the level set. So now the question is, what is the strategy in which order you should reconstruct the level set of your function? So one natural way is to use a dyadic approach. I mean, it's a very basic idea. It says, if you know your solution lives between those two bounds, then you start with the middle. So it means for each pixel you ask, I am above or below? So you can discard half of the space, and then you do that again, you cut in two. So you have a logarithmic number of operation you need to do to get a precision of epsilon. Now I'm not going to describe that, but you have much more complicated way so that you can set epsilon to 0. And you still have a polynomial. I'm not going to describe, it's more about computer science, but the thing is, you have a strategy to get exactly epsilon equals 0. So let me show you a demo. So this is a standard, denoising problem using TV. I have an image. I put some noise. Here you have the original image. And so you get the exact solution. So this is exact solution. Here, why exact? Because if your original data are rational, okay, so assume Gaussian noise, but I do an approximation here. If you give me rational data, lambda is rational. If oil is rational, then your solution will be rational. So I can compute that exactly with a computer. And this is the exact solution. And you can do that on standard computer in 0.15 seconds, 256 squared image. Okay. All right. Okay, just a little bit more about, okay, I got an image, I filter it using TV, so I increased the regularization. And so we got several algorithms, but the idea is the time here is that you have, a dependency on how strong you regularize. So here I'm not going to talk about that, and I cannot say a lot about that, but you have a kind of strong, dependence on how strong you regularize the image. But importantly is, if you multiply the number of pixels by 4, then you see that more or less you're multiplying the number, your time results by 4. So essentially you are almost in linear time in practice, again, in practice. I cannot prove anything in theory. In theory it could be n to the 3 or 1.5, depends on the Maxwell algorithm you are using. In practice, you are much below, much below. It's almost linear. So what can you do with that? For instance, you can do anisotropic mean curvature. So we use the scheme of Amgren et al. And the idea is the following. So you give me a time step, and you give me an initial curve, and I compute the sign distance for every point to this curve. So here it will be negative inside and positive inside. And you want to find the set A that minimizes this energy. When you take the Euler-Lagrange equation of that, the perimeter will give you the curvature, and here you have a distance over time, so essentially you will get the speed. So every point will have to move with the speed that is proportional to the mean curvature. So this is one way to make a curve evolution using anisotropic mean curvature. So if you do that, so you say, cool, I got a perimeter problem, I use my graph algorithm, and then you get stuck. You get stuck because of the discretization of your grid, right? I mean, you do not have enough precision, spatial precision, because of the discretization of the grid. So you need something subpixelic. One way to do that is actually not solving the perimeter problem, but solving the TV problem associated to your geometric problem. And now, once you have the TV solution, then you can do an interpolation to get subpixelic. So you can get the zero of your curve, which is an infinitesimal displacement of your curve using mean curvature, and you do that again and again. So let me show you what you get. Okay. So this is anisotropic mean curvature. So at the end, it means, exactly, it means that you are not isotropic. So when you do that kind of evolution, you should converge toward the Wolf shape. And if you are using anisotropic TV, then that should be a circle. So all curves should converge to a circle. And this is not what we get. We are using anisotropic TV. It means if I have a 2D grid, what I did here is I take my 4 neighbors, and this is how I estimate my gradient, and I put L1 here. So your Wolf shape will be a square, the L1 ball, and not the L2 ball. And this is what you get. Okay? You have anisotropy. Here you do prefer those axes, and I mean, it's not isotropic.
Oh, you mean you're not using the square root of
No.
x squared plus?
I cannot.
No, but that's the definition of anisotropic.
Exactly.
Oh.
Exactly. Yeah, because what I'm doing here, it's on regular grid, but you can use any kind of grid. So then the anisotropy will depend on your grid. Absolutely. So one way to get closer to a circle is, so let me show you, is essentially you will put 1 on horizontal axis and 1 over square root of 2 on the diagonal. So essentially we'll get a polygonal, and you will get trying to get closer and closer to your circle. But you will never be isotropic. So here you see you get more circlish thing. So you can do that in 3D too. So here you have a cube. And so one thing also you can show is that if you are using non-isotropic TV like the one we are using, then if you start with something that is flat, then you can create some facet. And actually, this is what you see on the corner. So something that is flat can get disconnected with that kind of. And so here you clearly see that kind of behavior. Okay. So I got. Okay, you can do also crystal growth. I mean, it's essentially a mean curvature. Okay, so partial conclusion here is, So you can minimize TV. We did that with the CGL. We can extend that for surface evolution. So you can do also non-convex data fidelity. What I showed in the introduction, the non-convex noise, then you can still optimize that exactly, even if it's non-convex. I'm also giving what are the sufficient and necessary conditions for using that kind of combinatorial approach. But now you can ask, what's going on when you don't want to do a denoising problem, but for instance, deconvolution problem or compressive sensing or whatever, where your data is seen through A. So we did, okay, I'm not going to talk about that, but essentially you can use well-known techniques and you can plug that kind of TV algorithm into it. So, but there is nothing really original. So I'm not going to talk about that. No, of course not. No. You need to do, you still use a combinatorial approach, but on the inclusion property fails, of course. No. I mean, you can show the inclusion property if you have any convex, data fidelity, it's fine. The thing was, it's working for TV, which was not that trivial, to us at least. Okay, so now I will try to give you some insights about when you want to do some evolution. So it's following the flow of the total variation. And essentially what I'm going to tell you is just more graphical representation, drawing some graph, and to tell you how you can do the analysis and actually compute exactly the flow. So again, with the epsilon equals 0. So the idea is, formally, you want to evolve an image using minus the gradient of total variation. I mean, it's formally, because this is not differentiable. So you start from this image, then you evolve, and you get that kind of result. So essentially, you design a trajectory, and I want to compute the trajectory. So since it's not differentiable, then you need to generalize the differential. So you call that a subdifferential. So you give me a convex function, and this is this set. So essentially, what you're doing is, if your function is differentiable at a point x, then the set will reduce to, the gradient. If it's not differentiable, for instance here, then you're going to find, you want to look at all the lines that go through x and that stay below the function. So essentially, it's all the possible derivative that you could define at this point. So this is what we call a subdifferential. And if you give me a particular element, I call that a subgradient. So okay, you put sub in front of everything. So the differential inclusion is essentially du over dt belongs to this set, and you start with v. So here, since it's not differentiable, so it means sometimes when it's differentiable, then you have many possible directions to follow. So you can define many kind of trajectories. But we are interested in one trajectory. You can show that there is an absolutely continuous solution, and it is unique, of this problem. Essentially, you can write u of t as the integral of its derivative. Essentially, this is what it says. And you can also show that that trajectory satisfies that. So it means, essentially, this is the steepest descent. Okay? This is the steepest descent. So you project 0 to the set of all possible directions, and this is the smallest norm. So among all possible trajectories, I want the slowest solution every time. And you can also show that this function has a right derivative, but not left. And I will show you exactly what it means in terms of the evolution and from an algorithmical point of view. Again, I try. So what I'm going to do here is just to remind what we did. We had the computer science problem. Then we go to TV, and I'm going to say, okay, I never talked about subgradient. So I'm going to relate what is a subdifferential, a subgradient in terms of graph. And I want to draw pictures and to relate those quantities. So the thing is, again, you give me a graph. I have a node, I have pairwise interaction, so as before I had a graph, and I say, I define a discrete divergence. You give me a graph, I can associate a divergence. So essentially, you give me a node, and I look at what's in, what's out, and I make the difference. So once I have this linear operator, then I associate a gradient using the standard relation. So I have a node, two nodes, and now I have the difference. So I define my discrete gradient like that. So I can get my TV defined in terms of discrete gradient, and so essentially this is what I build. When I start to build my graph, then I got one interaction. So now I want to solve that problem. So again, the ROF problem, L2 plus TV, and I want to look at what's going on in the involution of this problem when I move the regularization term. So I had TV here. Now I say, what about data fidelity? Then I can introduce a special node S. I say the potential is 0, and then I got data fidelity, regularization term here. Okay? Data fidelity is always from the source to a node, an internal node, and the regularization is inside. And so you can start to build the graph like that. What's important here is that you have a difference of variable here, and here, since you put 0, you can say it's u of I minus 0. So essentially, what I'm saying here is that you can formulate the problem as a difference of potential. So at each node, I will have potential. I compute my discrete gradient. Then I have a function applied to that, and I just sum them. And I say I want to minimize that. So the optimization writes like that. And again, you got your optimality condition. Oops. OK. So now I need to express the subgradient in terms of graph. So OK, to be clear, here I have a graphical representation of the energy. Now I want to go to a graphical representation of the optimal condition. So it means in terms of subgradients. So for that, you need to express what is a subgradient of TV, so you can show that it's essentially the divergence of numbers, and those numbers are on the edges. So it's kind of technical. I mean, essentially, it says here that in 1D, your subgradient will be a set, compact, and closed. So this is what I show here. So what you can do, essentially, that if you have that, then every time you give me a TV term, then I can build a graphical representation of the subgradient. I mean, the subdifferential. This is the subdifferential for two terms that are interacting through TV. You have data fidelity. It was quadratic. It is differentiable, so here you put the value of the derivative. So again, I get that kind of structure for the representation of the optimal condition. Now, if you say, I want to check if U is an optimal solution, then from a computer science point of view, it means, can you define flows, value on the arcs, so that every value belongs to the set, right? And then it's equivalent to solving this. So finding a feasible flow, can I find a flow so that I satisfy my constraint? Here I got a W that needs to live here. Here I need to live there, so that it's feasible. Can I find such a flow? If yes, then it means your solution is optimal. So what, in computer science, we don't like negative number. So what you do is you generally replace, you remove the negative number, one edge into two edges, and here you put 0, L1, and 0 minus L0, just because you don't like negative number. And what you get at the end is that kind of graph, which is exactly the graph that we constructed before in computer science. So actually what we did in computer science, the very first part, is to construct a graphical representation of the subdifferential. And now what we want to find is a feasible flow so that we get the optimal solution. This is how we did build TV. So this is what we solved in the second part. So this is another way to construct that. Now, okay, 2 minutes. We're almost done. What I did before is equivalent to finding what we call a balance flow in this graph. So here you will have the subdifferential of TV. Here you will have your data fidelity. And here you have essentially no constraint. And now you can follow Tajan and say, what is a balance flow? It means you give me 2 points. And where is it? Okay. So assume you are like that. And you say if one is higher than the other, and if there is no way I can find an augmenting path, I mean sending some flow from one point that is higher than me to a lower one, because everything is saturated, then this is what we call a balance flow. And what you can show in that this definition is exactly defining, saying that you have the solution of the RF problem. So you have that kind of notion of balance flow. And now what you say is once you have the balance flow, which is the solution of your TV problem, then you have a nice way to tackle perturbation. When I'm going to move a parameter, then how the balance flow is moving. And using combinatorial tools, then it's pretty easy to check what's going to happen. Briefly, I had a solution. I increased the regularization a little bit. What's going on? Then what you do is you have a solution, you compute the connected components, and you separate them. And you have an optimal solution here. Now you're going to compute the projection of 0 onto this solution. That gives you a vector. And so you get that, you decompose, you compute the projection, you add that back. And actually what you can show is that when you had a balance flow, you have another balance flow, you sum them, and it's still a balance flow. So it means you still have the solution. And what you show is if I move a little bit in time, then I start with my solution, and I move along the projection of 0, along with the time s, h. So that shows that your solution is continuous, it's piecewise anything, you can show maximum principle, you have a right continuous thing, and actually what you did is essentially solving that. You can show that. You solve exactly the differential inclusion problem. This is the solution you wanted. Now just to give you the final idea of what is a right derivative, it is like that. Imagine I start with something like that, a simple connected component. It can break. So I'm moving, for instance, like that. Things are moving. And here, I had another connected component that were going up too. So as long as the time evolves, then I am still, the differential is constant. So it's okay, I can differentiate. And now you say, what's going on when the two connected components will merge? Then here, the direction can change drastically. So that's why before the two connected components are hitting each other, it's okay, you are differentiable. When they're going to touch themselves, then the gradient is doing something amazing. So you cannot have a differential. Once you have that, the connected components, then you go back to something regular. So that's why here, you have the right derivative and not the left one. It's related how the level lines are merging each other. And this is the critical time you are detecting. Okay. So what I presented, you can do optimization for essentially L2, L1, but it works also for any separable convex problem. For TV, you can extend that to non-convex optimization, and we're going on differential equations and actually also Hamilton-Jacobi equations to solve that kind of things, again, in an exact way. Thank you.
Is there any question?
So I was fascinated with this log 1 over epsilon thing.
Mm-hmm.
So the way that I understand it, and you may have to correct me on this, is that you have a large class of problems where that's sort of a complexity barrier. And then you say that, well, there's subclasses of that problem where you can be clever and remove that.
Exactly.
And then the next question is sort of where is the boundary of that subclass? Where do you sort of hit, what you theoretically can't beat?
I know. I agree. I would like to know.
But
I know,
thi-
but
this
this
is
is
some-
an important question.
But this is something which I assume that relies on heavy theory from complexity theory, right?
Yeah.
Because
at
showing
least.
that you can do and showing that you cannot do
Yeah.
may be completely different parts of mathematics.
Yeah, and also something important that nobody really talks, it's what is the underlying computational model? For instance, here all I assume is the integer model. I only sum integers. But if you are using floating point model, can you sum two floating point numbers with arbitrary precision in finite time? The answer is no, in practice. But we assume it's constant time, so it depends also on the kind of model you are using for the computation.
Okay, thanks.
Thank you.